In the last video, we learned about the horizon coordinate system. It's worth pointing out what the 0 points of each of those coordinates was. So for altitude, we measure that from the horizon, which means that the 0 point of that coordinate would be the horizon. For azimuth, we measure all angles starting from north. So north would be our 0 point when measuring azimuth. Now, if we look back at latitude and longitude, we can think more carefully about what were these 0 points that we used. Latitude is this measure of north or south on the Earth, right? And that's measured from the equator of the Earth. So the 0 point of latitude would be the equator. Now, I'm making this distinction north and south and 0 points more clear because as we look at this equatorial coordinate system or the celestial coordinate system, we have to think carefully about what are these 0 points and how are they measured, because it's a very different system from the horizon system. So the equator is our 0 point here for latitude, and for longitude, the east-west measurement, we said before that that's the prime meridian. What the celestial coordinate system does is it takes this same kind of measurement of latitude and longitude and it extends it outward into space. So let's take a look at what that would look like. Here's a map of the night sky, just like we saw a map of the Earth. In the celestial coordinate system, we again have just two coordinates, and these two coordinates can specify any location on the night sky. These coordinates, though, are called declination. That's the north-south one. Declination measures north and south in the celestial coordinate system. And then right ascension is the one that we use sort of east-west. Now what's interesting is that the declination is a measure north and south of the celestial equator. The celestial equator is if we took the Earth's equator and just stretched it out into space, right? It would cross the whole sky, our big celestial sphere, in this point we call the celestial equator along this line. All right, so if you were standing on the equator, the point straight over your head would be the celestial equator. All right, so it's a little weird. So we're measuring declination and right ascension. These are the two coordinates. And just like before, we can see these coordinates mapped onto our sort of sphere of the sky. Now this is different, right, than our horizon coordinate system, because before, in the horizon system, we were using our horizon and the direction north as our 0 points. Now what's important about this distinction is we're using these things that are fixed in space as our 0 point. We're using the celestial equator as our 0 point, and then for the right ascension, our 0 point is something that's a little complicated. We won't need to know, but the point is that these things are fixed in space. They don't change with an observer's location. By contrast, an observer in Michigan will have a very different horizon than somebody who's located in Kansas. Right? So they can't necessarily agree on the 0 point because the horizons will be different. So it's not that the horizon coordinate system is great when you're standing right next to somebody who has the same horizon as you. But if they don't, you need something more outside of your individual location, like the celestial equator, to be your reference point. Okay, so let's take a look at this. There's a few more things we want to see, and we want to look at it a different way. So before we saw that way of looking at the sky as a horizon coordinate, now we're looking at it as the equatorial coordinate system. So you can see that the equator on Earth is being stretched out to intersect with the celestial sphere, right? This line across is our celestial equator. And in the same way, we would say that the north and south pole of the Earth can extend out and intersect our celestial sphere. And that would make the north celestial pole and the south celestial pole. So just like we have these things on Earth, North Pole, South Pole, we have a north celestial pole and a south celestial pole. All right, so now we can kind of see how this is measured. Declination being measured from the celestial equator, it's kind of like what we talked about altitude before. It's 0 when it's right on the celestial equator, but then the declination goes all the way up, up, and so here it's about 45 degrees, and then we go a little higher, and all the way up to 90 degrees when it's right at the north celestial pole. Right, and again, we have the sort of direction being specified by this thing we call the right ascension. All right, let's just take a quick look and see how these celestial coordinates compare to our horizon coordinates. So this is two views of the exact same situation. Right now we have an observer located near Michigan. I'll put him right in Michigan. And this is what the sky would look like for this observer in Michigan using the celestial coordinate system. We have the north celestial pole, the south celestial pole, and we have the celestial equator in yellow. Now, this observer standing in Michigan, we can see the same things on that person's sky, right? From this vantage point, when we're standing here like we normally do, looking out at the sky, what do these things look like when we're not like looking out this super zoomed out view of the whole Earth? To an observer standing there, the celestial equator would be this yellow line around our sky. It's kind of tilted. This is for an observer in Michigan, right? And the north celestial pole would be right here, and the south celestial pole would be right here. Now, I said before that if you were an observer standing on the equator, that the celestial equator would be straight over your head. So watch this. I'm going to move our observer's location to the equator, and watch what happens to this horizon view. Right? So this is like what an observer would notice if they were traveling across the world down to the equator. Okay, you'll see that now this line marking the celestial equator is now straight overhead, right? Because the equator is extended out into space, and now the north celestial pole and the south celestial pole are right on the horizon. Now think for a second, where would the celestial equator be if someone were standing on the North Pole, for example? If you were standing on the North Pole, you're like way up here on the Earth, where would that celestial equator be? Let's check it out. So as the observer goes up towards the North Pole, you'll notice it's rotating, and to that observer, they're standing on the North Pole. The North Celestial Pole would be straight over their head, and the celestial equator would be all the way around their horizon. Now, why does all of this matter? As we try to understand how things move in our sky, it's helpful to be able to describe their locations to people. So I'm going to turn on the Big Dipper, just as an example. All right. Now, what we're used to is this view on the right. Someone's standing here on the ground. They see the Big Dipper. Right now, they would describe its location as something like, oh, it has an altitude of maybe 40 degrees, and its azimuth is between north and west, so we'd say maybe it's like 315 degrees azimuth. Now let's watch what happens as time goes forward. As time goes on, you'll see that, of course, the night sky is rotating with respect to the Earth, and so now the Big Dipper is in a new location. If I got to go a little further, I would say, well, now its altitude is maybe 10 degrees, and its azimuth is 0, because it's due north. So you see that over the course of the night, its altitude and azimuth of those stars is changing rather significantly. So one disadvantage of this horizon coordinate system, right, is that the location of the Big Dipper or any star at one point in time is going to be different than it will be an hour or 2 hours later. It changes. Of course, an advantage is that it's really easy to measure from the observer's point of view. Now, by contrast, look at our celestial sphere view. If I set time going, you'll notice on our celestial sphere, the Big Dipper is staying in the same location. It's just that the Earth is rotating, right? And so this is, in a sense, more accurate, right? Because the stars aren't actually moving around the Earth. It's just the Earth that's rotating. But one advantage here is that on our celestial sphere, on our celestial coordinate system, the Big Dipper's coordinates would never change. They'd always stay the same. So if I have an observer located in Michigan and I've got a friend in Hawaii and I want them to see the Big Dipper, I could give them the celestial coordinates and they would be able to find that location in the sky. Whereas if I gave someone in Hawaii, I said, oh, it's at an altitude of 40 degrees and an azimuth of 30 degrees, they would never be able to find it because it's different for their location. So naturally, whenever professional astronomers are identifying the location of an object in the sky, they always use this celestial coordinate system, right ascension and declination. And their telescopes are programmed to be able to find those locations in the sky. You really wouldn't be able to find, if you were just standing outside with your star chart, you wouldn't be able to find those right ascensions, locations, and declinations very easily unless you had a computer to help you find those locations in the sky. All right, so it can be a little confusing, I understand, but I want you to understand there's two different ways of specifying the location of an object in the sky, and they each have their relative advantages and disadvantages.